afternoon, everyone. I'm Dale Gann, President of Denver Area Gem and Mineral Council. Today's speaker will be Dr. Virgil Lueth. He is the director of the Museum of Geology down at New Mexico Tech. And if you haven't been down there since 2015, you need to go. It's a spectacular museum now, and I always enjoyed it, but the last iteration, it even has thunder eggs. So it's an amazing, well, I say that I'm an agate guy, so as soon as there was thunder eggs, it's like, man, he's top shelf now. So if you would, everyone, please give Virgil a warm round of applause. Thank you.
All right, thank you. It's working fine. Very good. Do I have to do anything to make the slide show up? Push the first button. All right, there we go. Well, this afternoon, I'm going to take you on an exploration into the cause of color in fluorite. I'm not going to tell you what causes the color of fluorite. We're just exploring it, okay? It's a pretty complicated subject, but I'm hoping that you get an appreciation for how the color forms, why the variations, and what it's trying to tell us, okay, geologically. I really want to compliment the program committee. Whoever set up the program and put Peter ahead of me was brilliant, because I'm going to rely on a lot of his ore deposit models, and I didn't put them in my talk, but we'll talk about those kinds of things too. So I'm going to start off with acknowledging my co-author, Kelsey McNamara. She's our curator at the museum. Thank you, Kelsey. And I love to tell people, you know, I work for the New Mexico Bureau of Geology and Mineral Resources. There's 7 words in our title, and it happens to correspond to the New Mexico Institute of Mining and Technology. It has 7 words in it too, okay? But my title supersedes it. I am a senior mineralogist, economic geologist, director of the Mineral Museum and X-ray diffraction lab. That's even more than 14. Whoops. Yeah, so anyway, I just think it's kind of odd. A small state like, you know, population-wise like New Mexico likes to have big words in all their titles. So anyway, that's a little bit background there. And I want to introduce you. The first one we're looking at here is this Arango Namibia fluorite that I call Optimus Prime, because it looks like his head. You know, if you guys ever watched that movie, The Transformers, right? That's kind of what it looks like to me. But what I think is really fascinating is this isn't a play of light or anything like that. This particular, whoops, I'm doing it wrong. The zoning in here and the structures in here are just really fascinating when you take a close look at it. So it shows all the complexity that's going on in a single crystal as it grows. And perhaps we can find out what it's trying to tell us. So I'm going to outline my talk real quickly for you, just as we're going to introduce you to fluorite, which you know already, and then we'll look at some colors of fluorite. We'll look at the physical causes of color, and then we'll look at what I call geochemical causes for color, and even some geological causes for color, which I don't know if people can consider, but it's really kind of important into why we see some of the things we do. So I also want to start out by something I used to watch Saturday morning cartoons, and there was a show that would educational, and it would come on and say, sit back, we'll have some fun, and if you're not careful, you might learn something before it's done. That's for you guys, okay? Fluorite derived from the Latin fluor, to flow, an allusion to the idea that it was used as a smelter flux. It's the origin of the term fluorescence. It was an experimental accident. A pinhole of light was coming into the laboratory and it hit a fluorite crystal and it fluoresced in the dark, and that's how it was discovered. It's cubic, typically in cubes and octahedrons or multiple combinations, but can be reniform, stalactitic, and massive, hardness of 4. And what's unique about fluorite among the mineral world is it can be any color. That's really weird when you think about it. Most other chemical compounds have particular colors that are inherent to the elements that make them up. Fluorite, calcium fluoride, possesses the ability to have all kinds of colors. What is that? And just to show some illustrations, I'm going to show you people a lot of New Mexico specimens, not because I'm provincial, okay? But because they have a wide range of colors and I know more about it, and I know where it came from, and I know a lot about the geology of it. I know some of the geochemistry of it. So this way I can tell you a story that I know for a fact where like if you go back to the Orongo specimen, I'm not that familiar with the geology of that place and the ore deposit itself. So I wouldn't be able to try to understand what's really going on in the context of things. As a scientist my whole life, I've always tried to keep things in context. And I mean context, that's not only do you do an analysis, but how does that analysis fit in the real world and the geological world we see? And it's in that context that I think maybe we can find some things out. And I want to show you this really risque fluorite for a second. This is what we New Mexicans call X-rated fluorite. See the little X's on the top of the terminations of those octahedrons? They always make this little black X, and Betty Tlush of Carousel Gems and Minerals always sold this as X-rated fluorite. Sold off the shelves when you call it that, right? It's not about what they look like, it's how you market it. But anyway, that's it. And this is kind of an interesting one too, because these are octahedrons that are modified on the edges by cubes, and fluorite can never seem to get a decision as to what color to be or what shape to be, it seems, okay? And this one has that combination, then it's got the combination of colors in it. And so from the Gila fluorspar district, and we'll get back to these kinds of things in a little bit, but a classic New Mexico locality. Let's get it straight. Fluorite should be white or clear. If you look in the CRC, back in the old days when we used books, that was that giant chemical reference, and you could look up everything about any compound and it said it's white or clear. But now you can do this with the internet. But I always loved the CRC because it was so thick and heavy, it kind of made me feel comfortable underneath it. There's all that knowledge there. You don't get that anymore in front of a computer screen. But anyway, this piece was given to us by Joan Massaguet from Asturias, Spain, is perfectly water clear. And that's unusual for fluorite, which should be white or clear, but typically takes on some color. So obviously, when fluorite displays color, something's wrong with it. It's not a pure substance. It's not showing us its characteristic behavior. So there's a couple of examples. This is a newer one from a gift from Bill Marble, ex-tech student. This beautiful little fluorite right here from the Turk mine that shows a gradation of color from pink on one edge to green, sea green on the other. And then this is a Mextec specimen from New Mexico, the hexoctahedron on quartz with a rosy purple color. So colorless fluorite, I said, is kind of rare. It should be colorless. And I have a question about this specimen. Is it or was it really? Was this fluorite really clear, or has it been bleached out by the sun and collected on the surface? Don't know. This locality is kind of obscure, but the collector who collected it himself vouched that that's where it came from, and I kind of believed him. So this particular one from El Cuervo Butte is one of the few clear New Mexico examples that we have. And then they go kind of clear to purple. This is another one of those fluorite hexoctahedrons, but this one's a monster. It's almost a golf ball in size. This is from Gary and Priscilla Young. I don't know if Gary collected this one himself or if he bought it from someone, but it's probably the finest example of that particular crystal form from Hansenberg as far as size goes. And of course, purple, a classic color for fluorite. This one from the Pine Canyon deposit. Another one of Gary and Priscilla's specimens, a beautiful perched octahedron up there on the matrix with quartz and other purple fluorite. Some old pieces that we received from a recent donation actually has a lot more green material in it than we typically saw in these later examples that were mined at a later time. So early Pine Canyon material often had a lot of green component to it that we don't see too often. And of course, the combinations of purple and blue, these beautiful phantom crystals from the Fish Stick prospect from just a few years ago, excuse me, show this beautiful cubes with the purple cores going out to blue outsides. And the bright green specimens from another one from the Gila fluorspar district. These specimens are very large, and it's kind of reminiscent of the Wise Mine in New Hampshire as far as the colors are concerned, and in some ways the habit, except the octahedrons are much better. But everyone should really appreciate the fact that many of these beautiful green octahedrons were under an ocean of quartz, and they've been taken off the outside. So they don't usually come out of the ground nice and clean like this. And there's the mint green varieties, and this one happens to be from the Hilltop Mine at Fluorite Ridge down by Cooke's Peak. Not the place where we're seeing the Cooke's Peak stuff that's for sale on the floor right now. This is a little further south of there. And this piece looks like it might have been a scalenihedron, a calcite that was replaced, either epimorphed or replaced on the edges. And it's this beautiful sea green color. And I'm picking particular shades of fluorite here because we're going to look at chromophores later, and that's why I'm setting you up. You know, everything is planned to brainwash you completely, and then when you're gone, you have everything you need to know. Okay, and then there's these yellow fluorites, classics from the Illinois area. Another piece from Bill Marble, an ex-tech graduate. Neat little piece here showing that beautiful yellow with a light blue outer edge and a little bit of sprinkling of calcites and barytes on the top. And bright, fairly orange material from Wolfsendorf, Germany. This one happens to be from the C.T. Brown collection, which was one of our founders of the museum, as well as the re-founder of the museum after the fire. I was impressed to see this piece because this locality in Wolfsendorf, it has a lot to do with what I'm going to talk about today. The research that was done at that deposit is pretty cool stuff. And they talked about this orange variety, and the first thing I thought of, whoa, where do we have an orange one in the collection? And so we go in the reserve collection, and lo and behold, we have an orange one from that very locality. So this talk is even cosmic. Everything's coming together at the very end. And then the red varieties that are from Lagenstock here. This particular one is from Switzerland, from Al and Betty Tlush. Got a little green corner, and the rest of it's the red or pink that is characteristic of the alpine cleft deposits. And this is one that started this whole exercise I have in trying to learn more about what do the colors and forms of fluorite have to do with each other. Because when Dave Bunk asked me if I would give a talk last year that we didn't have here at Denver, he asked if I would talk about the colors of fluorite. And he mentioned that, you know, those darn red fluorites from Europe are always octahedrons. Why is that? Yeah, well, that's Kelsey's hand. So Kelsey, hold up your hand for Ed, and that's about how big it is. No, she's behind you. Yeah, that's right. I didn't put down measurements for the ones that were in her hand because I just thought, you know, she has a dainty hand. Sometimes it's a little dirty, but it's all right. But anyway, she was careful to clean her hands for this one. So anyway, that's the spectrum we're talking about, and they even get to be brown, like the stuff we see here from Ohio. That particular piece has that weird iridescence on the outside surface that kind of gives it that blue rainbow or almost a Schiller kind of effect. And I like that too because that's a physical cause of color, not a chemical one. And I just wanted to kind of have a chance to just illustrate a lot of ways in which color happens in things. And what's really kind of cool about fluorite is variations in color happen at lots of scales. Very large crystals, like this giant one from Elmwood that sits in our atrium now. This is before it had a place to live in our atrium. It was sitting in the back room and just keeping cool. And there you can see the yellowish in core, and then it gets darker purple on the outside. And then the variety of colors that show up in these beautiful Cooke's Peak fluorites that when you facet them have really unusual color patterns. Most of the time we're used to seeing phantoms in fluorites and not these patches and broad brush type things that we see here. These are kind of unusual in a way and hard to explain, but I might have an idea that you could always shoot down. That's fine too. So real quick, we're going to talk about the causes of color. I'm going to rely very heavily on Kurt Nassau's work from 1992 and other things because he pretty much wrote the book on color and how it works, okay? And there's the full reference there. And he talks about at least 15 physical and chemical causes for color. You ever think about that? There's 15 ways you make color. I never thought of that. You know, I gotta go step back here, another little story. I kind of digress. As I get older, my attention span gets shorter. But I have a farm out in the valley in Socorro, and we have hundreds, if not thousands, of hummingbirds, okay? And we actually went through 350 pounds of sugar this summer feeding those little sugar vultures, my daughter calls them. And while I'm making all that juice, a gallon at a time, I color it, not because they like the color. They could give a darn. White's fine with them. Kind of like real fluorite. It would just be clear. They wouldn't care. But I color it because it's something to do that's fun, right? And you mix colors and you try to recreate colors. And there's different kinds of colors you buy at the store. Some work for mixing and some don't. And I found that totally amazing, and that it's kind of how color really works. But it's in a kind of a backwards. We'll get to that a little bit, but I'm just telling you, I think about this all the time with those hummingbirds, and about how do we make these colors. So anyway, 15 causes of color. Vibrations and simple excitations. Everyone knows a flame has a color. Gas excitations like neon lights or even lightning is considered to be a gas excitation. And vibrations and rotations. This is what makes blue ice. Okay, so that probably in glaciers and things like that, when you see those beautiful blue ice things down in Antarctica, that's what's causing that process. It's the vibrations of the bonds in the Mickey Mouse molecules that are sticking together by van der Waals forces when it gets cold. And then there's transitions, and these are the most important ones to fluorite, okay? And these generally involve metal ions or ions with high field strengths. Okay, that means they're kind of complicated. They're heavy atoms. They're down in the rare earth range and things like that. Okay, or they're metal ions. So that basically, we'll talk about that in a little bit. But those are the ones, the biggest culprits down here. And there's different ways in which they do their thing to make color. That is mainly shifts in their electron shells that causes absorption. And how those electron shells are perturbed are when they see their next nearest neighbor, and they start trying to share an electron here. Hey, buddy, can I borrow your electron for a little bit, and all this stuff. And they change their valence state, not their valence states, but their energy levels. And as they change energy levels, they absorb light or they emit light. And that's kind of how we start making colors. And then, of course, at the bottom are the geometrical and physical optics, dispersion, that's the fire in gems, interference. We talked about that before, at films and cracks, Scattering. That's what happens why we have a blue sky. And then when the sun gets low in the sky, we're actually running light through a longer amount, more scattering happens and it turns red. Okay, so that's really what's happening there. Scattering actually is getting to be considered to be a little more important in the mineral world than we initially thought. And I'll talk about that in a little bit too. And of course, then there's diffraction concepts. And of course, light is broken up into many different colors. And the important thing for you to remember here is white light consists of all colors, right? So when the lights are white, we're seeing all the colors, and that's what we've got, okay? And then what happens though with this light is that when it gets into a mineral, sometimes it interacts with those electron shells around atoms, and some of it gets absorbed, some of it gets emitted. This is when I'm making the hummingbird juice. Because when you absorb certain light bandwidths and leave others behind, you create a new color, don't you, from what you started with, or you create a color that's unique to that thing. So that's the thing to remember here is this is my hummingbird juice palette, and now we're going to see how we can make it. Fluorite and all ionic crystals. We like to think of crystals as perfection, wonderful things. They're really not. Nothing's perfect, okay? And in this case, fluorite sometimes misplaces a fluorine or it misplaces a calcium, and they get a little stacked up in places where they shouldn't be, and then there's spaces left behind, and depending on how those things get stacked up and who's doing the stacking, they're called Frankel or Schottky defects. These defects in a crystal don't necessarily impart color. Okay, the defect itself does not cause the color, but it produces a situation that can. So that's what these things called F centers. So if we still have those defects, and we start cooking our fluorite somewhat. And I mean cooking it, I'm not talking about heat. Generally, we're talking about radiation. Radiation bombards your fluorite, and those electrons that are around the calcium and around the fluorine, and mainly around the fluorine, get knocked off. One of those lone pairs goes knocked off and goes into the hole and becomes a vacancy. It fills the vacancy with electrons, okay? Those electrons are very ready to take light and absorb it in different ways, okay? And so if this thing gets irradiated enough, it starts to create what we call color centers, or F centers. And these colors can be various ones. They're usually blue in fluorite, okay, typically blue. And so then they sit there, but they're kind of ephemeral. Because if you take that fluorite and you heated it, or you put it in the sunlight, it bleaches out. These particular types of color centers, or F centers, are a little more transitory. So that's why people don't put their beautiful blue Hansenberg blues in the window for very long, because they become Hansenberg whites, right? And we know that that's what they're supposed to be. They're just striving to get back to where they're supposed to be, right? They get back to perfection. But in this case, that's one way in which fluorite gets colored, and we see this a lot. And I've killed a few fluorites myself. I don't say I killed them. I returned them to their natural state, okay? And that is, here's a classic example, a Nacke mine specimen that Ron Anderson brought to me one time. I told him where to go collecting, and he came back and he brought this cooler that opens up in the top, and he goes, "Is this what I was supposed to look for?" And he said, "Well, yeah." He said, "Well, I thought since I found it where you told me where to look, I thought I'd offer it to you first in the museum." So it did get to go to the museum. And in its early life, it was really, this is showing up a little bit more purple than it really was. It was really more steely blue. And I thought when I had this picture in here, it was blue, but now it's in this light, it's looking a little purple. See, that's the trouble with color and light. Depending on the person perceiving it, your own spectrometers, okay, and also the type of light or type of bulb we're using changes colors, okay? So anyway, that's just the complexity of color. I want you to remember that's really complicated. But anyway, this guy sat in the museum sat there for a long time now, and started out this nice steely blue, and now it's kind of a pinky purple, okay? So, and we had filters on the lights to cut down the UV and all this stuff. It doesn't matter. The Nacke stuff's notorious. One time I was out hunting for the elusive mineral jarosite, the greatest mineral on this planet and on Mars. And I was up at Nacke, and there was these big knots of calcite on the ground, and I'd crack them open, and there'd be a big, blue, beautiful fluorite inside that calcite. But I was not looking for fluorite. I was looking for jarosite. So I kept going down the hill to the next mine. And then I came back and said, maybe I should collect that and burn that calcite off that. That'd make a great mineral specimen. I looked, I knew right where I was, and I looked and I looked and I looked. I couldn't find it, and I realized that thing had turned clear within the 15 minutes I was gone. So that's how fast that F center disappeared in that particular sample. And that's kind of what's happening here. Even with our best intentions, we couldn't quite do that. But what I find really cool about this specimen is that pinky purple that's still there, that's still there. Why? That's not an F center. That's got to be something else, okay? And we're going to keep going into the story, and we'll see that a couple of times. So a compilation of chromophores. This paper by Dylan Weber in 2010 really changed the way I look at fluorite deposits, because these guys did a fabulous job. They did all the kind of work you need to do. They did fluid inclusions, they did isotopes, they mapped color, they mapped forms. They went through and they compiled every paper that had ever written about fluorite and what colored it. Okay, and then what they did is they looked at it and they said, well, it turns out that at this deposit in Germany has almost as many colors of fluorite as Hansenberg, New Mexico does. It actually has more. I mean, it has a whole spectrum. And so they put these together for us, okay? And real quick, you can see that the blue color, some people claimed it was the iron 2+, 3+ ratio plus a little bit of copper. Another paper said colloidal calcite. Some people talk about yttrium-associated chromophores or centers, and other people ascribe it to rare earths. The brown colors are because they're full of organic compounds, and that's typical in many of the mid-continent pieces, by the way, petroleum and other things like that. And they also talked about manganese and 2+ and 3+, and perhaps thorium for brown. Yellow by europium, or iron plus rare earths, or these unusual oxyfluoride compounds that are happening with some of the, are getting incorporated into the crystals. The yellow-green is considered to be a yttrium-cerium type of situation. Green is caused by colloidal calcium, excuse me, or iron and all these things. So you can, or samarium. So you can see these different elements coming to pass here. Orange is caused by manganese in this one page. If you ever want this, I can send you the list of references that correspond to this. It's hard to put this on a thing. You're not supposed to talk about a table when you give a talk anyway, but I made it colors, so it's kind of cool. And then so there's pink and red that caused by the iron 3+ or yttrium oxide, organic compounds, or chrome plus manganese 3+. You know, chemically, it's a mess. Nobody's really come to a conclusion as to what anyone is in particular. And then this purple to black colloidal calcium. Colloidal calcium. That's an interesting one. Okay, how do you make colloidal calcium? Well, you're in an ionic compound, right? You got a positive cation, which is the calcium. You got negative anions, which are the fluorine. And if you irradiate them hard enough, maybe, you can kick an electron all the way to calcium. Calcium grabs it and becomes metal. Whoa, that's a cool concept, you know? Is it real? It's kind of cool, you know, but I don't know. We'll talk about that in a little bit. Haha, this is the worst part. Sorry, guys, but this reminded me back of, I took this class back in 1988, I think, when I was in inorganic chemistry, molecular orbital theory, right? You guys ever take that class? If not, you know, that's cool because there's funny little shapes you get to draw, okay? But the point that I'm showing you this for is that atoms and their electron shells, you know, we talk about the Bohr model of the atom, and you'd put the nucleus in the center, then you had all your electrons going out in like the solar system. It's not that way at all, right? Actually, atoms have shape, okay? It's kind of a weird thing, but atoms have their own shapes, and they only can shape themselves certain ways. And so when you have just something simple like helium or hydrogen, it goes around in a sphere, all right? And then as you start making more orbitals, they have to go in funny little shapes. They become little doohickeys and donuts and things like that, okay? And so as the atom, you start making more and more complex atoms, read rare earth elements, you have to make these weird little balls that are all pokey and bumpy, all right, in electron space. Not that you can ever know where that electron is, right? Heisenberg said you can't, but you know they're there somewhere. But anyway, what this illustrates is that on the outside of many of these high field strength atoms, you've got little places where electrons are hanging out on the edges, far from home, right? And because they're that far out, their nearest neighbors can kind of pull on them a little bit, right? And excite them, all right? Or change their valence states. And when they do that, what do? They start absorbing light. So that's what's happening in these high field strength elements like the rare earths, even copper, any iron, same thing. That's why they can do this, okay? Because they have these little bumps on them, and those bumps are providing access to electrons, or at least for them to be perturbed. Done with that, okay? But what Dillon and Weber did, though, in their great study, or the study that I liked, I don't know if it's great or not, they actually looked at all the rare earths in all the different colors, and they looked at all the transition metals, or the metallic ones, in their fluorites, so that they could get a sense of what's the chemical variation of one color of fluorite to another. Kind of a neat thing. They didn't prove which element or which particular groups of elements are necessarily imparting the color, but they're providing us clues as to which ones we might want to look at to make colors. And so the lab rats in us could then go, well, I'm going to go see how cobalt does this to to a fluorite, and I'm going to start synthesizing fluorites and see if I can make them yellow or orange. That's the point. Okay, so this is kind of a neat starting block, and if I were a younger professor with a stable of students, I'd make them all do one, right? So anyway, in a way, this is from NASA's book, and it's real quick, and I just want to, this is how it works. Light coming in excites electrons into different bands or different places where they orbit around the atom. When that happens, they have to fall back down sometimes, and in that process of going up and falling down, you get absorptions going on. And so if you're looking at the spectrum of colors here, this is red down here and violet down here. All these different energy interactions actually cause absorption of green, absorption of violet, a little tiny bit of blue transmission gets through and a lot of red transmission, and that's why a red ruby is red. Okay, and you can do this with all minerals and with trace elements and how they're doing that thing. Chrome is the big one here. Chrome 3+ is what causes that. The other thing that Chrome 3+ does is it causes a bit of fluorescence, natural fluorescence, right on top of the strong transmission line, so it adds more red to red, and that's why they're so red. But that's also why rubies are a touch blue sometimes, right? Have you ever noticed that? Sometimes they get a little to the purpley side sometimes, especially the cheap ones that you can buy anywhere. And that's the cause right there. That's what's happening on. So you could do this with every one of these things. So think about those electrons out there. Think about those holes that are full of electrons and thinking about them always changing their energy levels, absorbing or emitting light of different wavelengths to create your hummingbird juice. They also went in and did a bunch of fluid inclusion work on these fluorites of different colors. Okay, and that's what they look like. Spent some of this doing this as a kid too when I was a young graduate student, and it was tedious work, but it helps you to know something about the temperature and the salinity of the solutions. Peter was talking about saline solutions and things like that, and they're basically tying together what makes these deposits form and what's different about the different stages and colors. And we can do stable isotope work. This is stuff from a student at Tech, Greg Hill, who did a bunch of fluid inclusion work, did fluid inclusion work and did stable isotopes on it to look at the relative number of components of meteoric water versus magmatic water in these systems. So we're mixing water from magmas and we're mixing waters that come down when it rains and gets heated down deep. And you get an idea of how the waters are interacting to make these things work. And ultimately, doing all those things, you create an ability to look at the evolution of an ore deposit. That's the basis for all this is all about. And this is kind of a summary diagram from Dylan Weber's work at Wolfsendorf, Germany. And it summarizes basically what they observed in this place. Now, what I want to point out is I'm talking about this thing called PTXC. Pressure, temperature, composition, and chronos. Okay, and chronos means time. Okay, they didn't do any chronos in their study, but that's kind of what I do in fluorite deposits for part of my living. So that's putting the whole thing in together in time and space and chemistry. How did this happen? And what I found fascinating was they noticed that high temperature fluorites tend to be octahedrons. Low temperature fluorites tend to be cubes. And there's all these oddballs in between, evolving their way between high temperature to low temperature. And that they even insinuated that they could see that there was rapid pathways and there were slow pathways in these deposits of making these crystals would form at high temperatures, and as the system cooled down, they'd make new forms, okay? And so I found this to be fascinating because, yeah, you could go into a deposit and look at the fluid inclusions, get their temperatures, look at their forms. How about the color? Does the color follow form? That's the next thing they say it did, or they thought it did. Oh, back to color, F centers. I'm going to just do this because I want to go back to colloids because we did some experiments with salt. You know, these are the famous blue halites from Carlsbad. And, you know, we did some experiments. We said, well, how blue is blue? Is that blue permanent or is it ephemeral? So we were blasting them with short wavelength UV lights for various periods of time. And the blue halite stays blue. The purple halite or the yellow halite, which is also irradiated, goes white with shortwave radiation. Then I ran across this paper by Levy back in 1979 where they were actually purposely blasting halite with high doses of radiation at Brookhaven Laboratory. Why would they do that? It's called the WIP site in southeast New Mexico, where we store all our radioactive waste in salt. They wanted to see what salt happens to salt when you blast it. And they were making blue fluorite because whether they blasted it long enough, they started developing a new absorbance which corresponded to blue, which they called the colloid band. They believed their irradiating the sample was blasting an electron onto sodium and making sodium metal in the halite, and it became a colloid. When that happens, light coming in hits that colloid, and what does it do? Blue sky, scatters. And the blue halite is a scattering phenomenon, but once that sodium atom had its electron, it never gave it back, and it stays blue. It's permanent. So this might be a similar type of thing that happens in fluorite, okay? And here's where Chronos comes in, right? Time, you know, we're not blasting them like we are at Brookhaven with high doses of radiation. All we can do is use a little bit of soda, a little bit of potassium that's laying around in rocks, right? In volcanic rocks or in granites. But over geologic time periods of millions of years, you can attain great doses of radiation and maybe make colloids in your fluorites. So that's the point I'm trying to make right there. So, first pass. How do you, how can we maybe see if this is true or if this is real? Okay, well, you take an inventory of what's out there in the world, right? And you start looking at the various types of deposits, their ages, and the fluorites they contain. So we're going to visit, where Peter didn't do pegmatites in metamorphic environments, but just think of the Alps or the Himalayas, okay, when we're talking about that. Giant place where plates are coming together, getting regional metamorphism, so you got big zones of temperature and pressure that everybody's feeling over wide areas. And then you can go to magmatic hydrothermal systems and Mississippi Valley type systems. And then we're going to step into rift environments because they really are special. Not just because I live in a rift, but I think they're special for fluorite. So anyway, we look at specimens from these old pegmatite metamorphic terrains or even the Alps or places where we still see these octahedral pink fluorites. I still don't know what makes them pink, but my first hypothesis was going to be that I think perhaps maybe they were colloidal and we just haven't recognized that. That's late sunset color, right? Kind of deal. I don't know. That's a thing to pursue. But this is like the only environment where we see the reds, pretty much, except the Mongolian pinks, which are a little different, but they're a high temperature metamorphic skarn type deposit. So there's something kind of going on there, but it's also an octahedron. Almost always an octahedron. And then down here in South Africa, we got these beautiful electric green fluorites. We recently got this from Nancy Attaway, and the gentleman who sold it to her was telling her they had it tested and it's full of niobium. So this might be an example of a niobium color center in these blue-green electric fluorites from South Africa. Speculation, but it's something they did some analysis, and that's the first sign. They're not red, and these are really old deposits too, by the way, not young. They're a billion years old. Now we go to magmatic hydrothermal, like the Last Chance mine. I put this one, another thing I want to mention during my talk is that a lot of these specimens you're seeing in my talk are on display in our case upstairs. So if you want to visit them in real life, they're there for you to look at. And this one here I put in because I didn't need a scale bar, Ed. It's as big as my head, right? That's pretty damn big, I think. So anyway, and again, these are deposits that were formed on the margins of calderas in the Gila Wilderness area. These are magmatic, hydrothermal, high temperature type things, and a lot of the fluorites in the Gila are octahedrons. High temperature, octahedrons. Dark green. I don't know what's coloring this guy, but you have a silicic magma chamber down below spewing some of these metals out with their hydrothermal solutions. And here's another one that's really interesting, another octahedron, really rare specimen. There's not very many fluorites from San Pedro, which is a famous skarn deposit just north of Albuquerque. But these are dark purple octahedrons sitting on specular hematite, garnet, and lawmentite. And it's a high temperature assemblage. That's a high temperature fluorite again, octahedron. Purple. Well, purple can be a colloid, but I don't know. We'll see. And then we go to Illinois, MVT deposit. We're all pretty familiar with the MVT. You walk out in the dealer cases here, they're all over the place. They're beautifully zoned. They're yellow, they're purple, they're black, they're blue, they're cubes. Cubes, 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 cubes. Low temperature. Why are they so zoned? Well, if anybody who knows about Mississippi Valley deposits, these are ore deposits that form during these large basin systems. They're tilted basins, and the hydrology, they're high on one end, come up on the other end fairly steeply. All the water, this is what Peter was talking about in the saline things down there at Moose Keys. You're moving water a long ways, and it takes a long time. But these systems are huge, and they last a long time. And they're huge, and they last a long time, and they're traversing through basement rocks and things like that. They're picking up a lot of funny elements on the way. And one of the things that fluorine is really good at, complexing transition metals and rare earths. It helps them go into solution. So fluorine is a natural, the fluorine in the hydrothermal solution is transporting the very metals that are causing the colors. And so if you can think about it, if these hydrothermal systems and MVTs have lifespans of millions of years, are you just seeing millions of years of new waters flowing over them with different compositions, perhaps slightly, that are causing this beautiful banding and variation in color throughout the Mississippi Valley type deposits? I'm throwing that out there as a possibility. So these are just reflecting different fluids. And you have time to put a different fluid through any time. It's not one-shot show. It lasts a long time. And so this yellow, and so that's an interesting, and another thing about the yellow, particularly about yellow fluorites, is the German researchers noted that they ascribed it to manganese, and they always thought it was the yellow color was a low temperature near supergene phenomenon. So this is barely warm water. This is fluorite crystallizing from fairly just warm water, not hot, maybe. Okay, now let's look at a rift deposit, and one of my favorites, Hansenberg, where I do have Chronos, by the way, okay, because of that wonderful mineral jarosite, the greatest mineral on this planet and on Mars. The earliest fluorites at Hansenberg are invariably sea green. Sometimes they're cubes, sometimes they're octahedrons, most of the time they're cubes. Some of them are very large. Stage 2, they start to modify. They become roundy. These hexoctahedral, trisoctahedral kind of things start showing up, yet they maintain their sea green and their beautiful fluorescence. And as time goes on, they get more goopy and strange looking, till finally they become these, right? And then they start turning blue and becoming cubes. And finally they are cubes and they are blue. And stage 5 are small purple. I don't have a picture of this because they're not very exciting little specimens. They're cute. They're very purple, and they're only about a 1/4 inch on an edge. They're very square. They don't have any modifications, but they're almost always doused in jarosite. Okay? And you got greatest mineral on this planet and on Mars. But what's jarosite got in it? Potassium. It's radiogenic. Those are purple because of radioactive things. And that's why the blues and things, there's radioactivity there. So we're seeing, some timing, and we're seeing some shapes things. So it looks to me that as time goes on, at Hansenberg, we changed colors, we also changed form. Okay, that's the takeaway there. Here's another deposit that you almost never see because it's on the White Sands Missile Range. We were fortunate to be able to go out there one time. Mike Sanders had been there too. This is the Bornstadt claim. beautiful dark purple cubes on quartz. When you walk to the dump, it's purple. The dump is purple. That almost, in a New Mexico fluorite deposit, that almost never happens. This is a color fast purple. It's by a chromophore, not an F center. Okay, so there's something in this one that's really making it purple. Is it colloidal calcium? Is it something else? Maybe this would be a good one to look at what makes something really purple, because this is permanent purple. Another one, Cooke's Peak. And I put this one in here because is it magmatic hydrothermal or is it part of the Rio Grande Rift situation? Well, early stage 1 fluorites there are blue cubes or blue-green cubes. Then they start going octahedral, turning green, and then they get coated with a purple octahedron at the end. Okay, and this particular specimen, this is called the Jolly Rancher, because it looks like an apple Jolly Rancher, look like Jolly Ranchers. Okay, can't help what people call things when they discover them. They gotta call it what they want. There are the blue cubes. There are the green octahedrons. There are the purple octahedrons. It's backwards this time, though. Now we're going from the cubes first to the octahedrons last. What does that mean? And the colors are changing with each generation. We actually have a student working on this right now. Cody Schwenk is working with the fluid inclusion temperatures on these things to see if we can unravel the temperature concepts. Yes? That's what we're hoping to see. That's what we're throwing at it. Exactly. That's exactly what we're throwing at it. And so this is going to be a test. Is this a magmatic hydrothermal? Is it a? I think it's a magmatic hydrothermal myself, and it's also one that started cool and got hot. So maybe I don't know, but that's where we're going with it. And then of course there's a last stage on top of all this, which is a botryoidal supergene fluorite, weathering fluorite essentially. And then, of course, here's the Zuni Mountains from New Mexico. A lot of unusual colors in the Zuni Mountains. Lots of unusual colors. Very electric again, more like the South African stuff. And, well, these are Rio Grande Rift type fluorite deposits hosted in Precam Proterozoic granites. Okay, so traversing all these old granites with lots of rare earths in them and stuff like that, there might be something to that. They're all cubes, though. This isn't very hot. Yellow cubes. Not Illinois, but they're yellow. And of course, even some late stage botryoidal stuff of a really unusual color. This is a teal blue, and that's an unusual color unto itself. Something we should take these apart and analyze them quick just to see what elements are in them to start speculating grossly about what we've got. And of course, even on the white sand, even on the Kirkland Air Force Base at the Highland Mary Mine, here we have a cubo-octahedral, multicolored, splashy thing again. And we know we're in the rift, we're in Precambrian granite. It doesn't quite know whether to be an octahedron or a cube. Is it just a higher temperature variety? But maybe taking these concepts of context in. So here's what I want you to take home. Pressure isn't too important in most minerals, okay? Unless you're in a metamorphic mineral itself, not for fluorite especially. But it appears, based on the survey of tectonic environment, the survey of fluid inclusion temperatures, that fluorite's form has something to do with temperature. Compositionally, almost all the color in fluorite is due to compositional changes. Nothing to do with temperature. Whether it's an octahedron or not, it doesn't matter. The color is not tied to a particular form, except the red ones. Don't know what that is, or is it because they are unique to that high-grade metamorphic environment, and whatever element's doing the chromophore there is where that goes on. And of course, we know that as far as time goes, the longer a fluorite sits in a radioactive world, the darker its color will get. Whether it's colloidal and becomes permanent color, or whether it makes it a deeper color of your F center, that's an important consideration. And conceivably, if we really got smart someday, the intensity of color could be a function of how long that fluorite's been in existence in its environment, okay? Much like we think the halites are down at Carlsbad. And just to bring this home, here's a bunch of Chinese fluorites showing a rainbow of colors. They're all cubes, right? color didn't matter to form, I don't think, in most fluorites. Only a few, perhaps. That's all I have. At the bottom of the hole. Thank you for your attention. Appreciate it.